right, good morning, everyone. Good to have you here again for this third week of Lorax and other eco-justice voices. That little Dr. Seuss character has helped us realize that we need to speak for the trees or the brown barbaloots or the Swami swans or whoever else is not getting heard in our environments. Dr. Seuss was one who kept raising awareness for us, and we just sort of dovetailed with his image to bring in the real life situations of why we need to pay attention to what is going on in our climate and in our world. We have a special guest today. Bill Middlecamp will be here to share a lot of information about how we impact our society and our world. But let me give you the introduction just so you know who you're about to hear from. Bill Middlecamp is a trained climate reality leader and is trained in En-ROADS. He's an ambassador for that. Bill has a BS degree in meteorology and an MS degree in computer science and is a commissioned United Methodist Earthkeeper. For more than a decade, Bill has participated in organizing and delivering dozens of presentations on environmental issues related to health, economics, science, and solutions to the harmful changes we are seeing. Bill is retired, congratulations, and dedicates himself to teaching about our degradation of the critical life-sustaining properties of the environment. Bill is also a director on the board of Dakota Electric Association, a rural electric cooperative. His presentation, I think, will be so educational for us. It will show the environmental destruction impacts which we are experiencing today, how we got to this point, what the future may hold. Following that, you, the participants, led by Bill, will experience this En-ROADS solutions. It'll be similar to an imagine together what our future could be. En-ROADS is a choose your own ending type of scenario or simulation that uses some of the best available science to compute and present possible results from choices in our energy, our food production, our land use, our consumer behavior that society is making, and choices we can make today. He will encourage your participation and questions as we go. Would you join me in welcoming Mr. Bill Middlecamp?
Thank you all for this opportunity to speak to you today. I'd like to begin with a prayer. Lord, may the words of my mouth and the consideration of these facts be pleasing to you and inspiring to us as we seek to understand our role in caring for your creation and sustaining the life-giving properties of our environment. In Jesus' name I pray, amen. All right, I'm gonna have three parts to my speech today. The first one is actually going to give you some climate science. I'm going to grab this and step out of the way so that I'm not standing between you and the screen. So I'm going to talk about the science so you can understand what are the physical activities that are actually happening. How does climate change actually work from a scientific perspective? But there's no math, so don't worry too much about that. And then I'm going to talk about some of the effects that it's having on the environment and who it's impacting. And finally, this En-ROADS, as you heard Pastor Jim mention, is a simulator which allows you to experiment with some of the solutions that have been proposed, that are being discussed, and see what effect they actually have. It's a very interesting free program that's put together by some very smart folks out at MIT, and it encompasses the science, the physical sciences that come to bear on this, as well as economics and business principles that take into consideration things like how long it takes to make a change in our systems, how it takes time to build up supply chains and so on. All right, So, first of all, the worldwide environmental energy balance is changing. We're going to talk about the physics behind that. What does this mean for humanity? What can we do about it? And what are the next steps? And I say please hold your questions to the end, but if something's confusing to you, interrupt me. I just want to make sure I get through the material. I have quite a lot of material. So go ahead and ask questions if something doesn't make sense. Don't let me rush past something. All right, first of all, little Gary Larson humor. Grandma's on the floor, and there's a cookbook there that says Recipes for Disaster. And it's a good example of what's going on in our world. We are doing wonderful things. We have many creature comforts. We have energy galore to make our lives great, and we've made tremendous advances, but we're using a recipe book that has a bad ending to it. And I'm going to talk about why that is. The reality is we don't have to use that recipe book. There are solutions that can give us all the comforts we want and yet sustain the environment that sustains life. All right, so worldwide energy is out of balance. First of all, virtually all of the energy we have on Earth comes from the sun. And I'm not talking about stored energy where plants grew millennia ago, millions of years ago, and now we're seeing that as coal and oil. I'm including that when I say that almost all the energy on Earth comes from the sun on a daily, continuous basis. The sun gives us 10,000 times more energy than all of the energy that we produce through digging up fossil fuels and burning them, or using nuclear energy and so on. Those are minuscule compared to the amount of energy that's coming from the sun. So what does this look like? How does the sun provide energy to the Earth? First of all, there's a physics property that everything that has warmth radiates energy. If you could see it, every one of you would look like a little light bulb because you're warm and you're radiating energy. The color of the light that comes off is dependent on the temperature. The sun, as we know, is very hot, so the temperature, the color of the light that's coming from the sun is very white and a lot of visible light. This energy comes to the Earth, strikes the Earth's surface and warms it, and then the Earth, in turn, because it's warm, radiates that energy back out to space. It is relatively cold, so it radiates in infrared, long-wave radiation that we can't see with our eyes. Okay? The atmosphere, which is primarily nitrogen and oxygen, is transparent to visible light and to infrared light. But the greenhouse gases are transparent to visible light, but opaque to infrared light. And there's a wide range of opacities and interactions with different kinds of molecules, but in particular, carbon dioxide, methane, and several other gases, including the manufactured gases, the so-called F gases, things like freon, they have an interaction with these long-wave radiation photons as they're streaming out from Earth. The balance, if there was no atmosphere and Earth was simply a rock floating in space, the average temperature of the Earth would be 0 degrees Fahrenheit. We would be an ice ball. Well, we wouldn't be an ice ball because there's no atmosphere. So imagine the moon is roughly, on average, 0 degrees Fahrenheit, because it's pretty close and it's experiencing the same incoming radiation from the sun. It can radiate that infrared energy out, the moon can, at the speed of light. And it stays in balance because if it didn't, if all the energy just came and stayed, eventually that object in space would become the same temperature as the sun, and everything would evaporate, right? We have to radiate the energy in order to stay in balance. With an atmosphere, as the energy is leaving, it only goes a short distance and it runs into a molecule that it interacts with. It heats up that molecule absorbs that photon of energy, warms up, And then because it has warmth, it in turn radiates that energy back out. When it radiates it out, it doesn't radiate it in the same direction, it radiates it in all directions. So half of the energy is coming down, half of the energy is going up. So instead of that energy flowing out to space at the speed of light, it hits a molecule, and then radiates again, hits another molecule, radiates again, hits another molecule, radiates again, and so on, bouncing its way around that unit of energy until eventually it reaches a point where the atmosphere becomes thin enough that it can then stream out to space. Because of that extra time that it takes to leave, the temperature starts to rise. It's kind of like a dam. Imagine if you have a river and the Earth is an island in the river. So the sun is like the energy, the sunlight coming from the sun is like the water coming down the river. It gets to the island and it flows past the island in balance, right? So the river, the shore, has a stable level. If we start to build a dam at the bottom, at the back end of the island, imagine we have a beaver and the beaver's dragging sticks out into the stream, putting sticks out there to slow that water down, the water starts to rise, right? It's the same thing with this energy. As the radiation is slowed down, the temperature rises and it reaches an equilibrium, just as with a dam. Eventually the water would raise to the level of the dam, and then you have just as much water flowing downstream as you have flowing in upstream. It would be in balance, right? But if you kept on adding more and more sticks, eventually that water would inundate the island. It would continue to rise, and that's what's happening here. We keep adding more greenhouse gas molecules, and that temperature keeps going up. Now, greenhouse gases are a good thing. As I said, without greenhouse gases, the average temperature of the Earth would be 0 degrees Fahrenheit, and there wouldn't be any life on Earth. But we're changing the balance point, and what does that mean? This is a chart that shows the global temperature starting 12,000 years ago. And what you see is we were climbing out of an ice age, and we bounced around a little bit, and then about 8,000 years ago we hit a stable point, and it has been quite stable since then up until the present day. During that 8,000 years, I mean, if you think about how old are the pyramids, how old are some of the oldest evidences of society and humanity, how old are those things that we find on Earth? Compared to how old humanity is. How old is modern man? I don't think anybody is quite certain, but I think somewhere around 100,000 to 300,000 years, maybe a million years. Humans were around a long time before we started to develop societies and build up the wealth that we have around the world. All of that development, so far as we know, has happened in the last 8,000 years when there was this very stable period in the environment. This is actually, I mean, scientists can go back many millions of years, and what they find is that this 8,000 years that we've been living in has been an unusually stable period in planetary history. All right, so we have built our cities, we have built societies on the margins where we can do so, where we can grow food, where we can use water, and so on. We've built all that wealth based on a stable environment that lasts for 8,000 years. If we change that, will we be able to continue to grow food? Will we be able to trust the water levels of the ocean and the rivers and so on that we live next to? Or will we have an expensive change that we have to adjust to something new? And will that be stable, or will that be continuously changing? This next chart takes a shorter period. This is just the last 2,000 years since the time of Christ. And again, you see that we were very stable with a slight cooling trend as we were moving into the next ice age. We should be, according to the so-called Milankovitch cycles, which have to do with how the Earth is rotating in space, kind of wobbles, and as it wobbles back and forth, it changes the balance of sunlight on the northern and southern hemisphere, and that gives us the cycle of ice ages. We should be heading into the next ice age, but instead, because we're changing the greenhouse gas concentration in the atmosphere, we are pushing ourselves into a warming period. Oops. Right here, this is what they call the hockey stick, because what we're seeing is a very dramatic shift, taking us into an area that humans have not lived in. A new area that humans have not existed in. All right, this graphic I find very useful. It's like a clock. As you go around, you have the months of the year, and every time it goes around one turn, that's a year. It starts in 1880, and it's going to run up to, I think, 2020. And what you see here is a green ring, which is 0 degrees, and that's based on the average temperature in 1950, okay? And the inner ring is 1 degree centigrade cooler, or 1.8 degrees Fahrenheit. And the outer ring is 1 degree centigrade warmer, again, 1.8 degrees Fahrenheit warmer. And as I start this, you'll see that the temperatures that are close to that middle ring, that 0 degree ring, they are white. And as you get in toward the center, when you have colder years, it turns blue, and as you go out to warmer years, it turns red. And you can see it's really quite stable until we get into those Dust Bowl years where we start to have a little bit of red showing up. And then it kind of goes back to more normal as we get into the 50s and the 60s. But when we get to 1980, that's when the variability in the environment started to really go significantly warmer. And you can see the red showing up here as we burst out. Now we're getting into the 90s, and then into the 2000s, the 2010s. And as it finishes, it's going to rotate so that you can see this from the side. And I find this to be very dramatic, because what you can see is that you've got what looks like a column. It's really pretty consistent up until 1980. And then you've got this dramatic upward growth. And it's clear that it's not a temporary thing. It's not a short-term thing. It's been going on now for 45 years almost. And it's going in one direction. I mean, that looks like a water tower, doesn't it? This is another animation. This is a so-called Gaussian or bell curve. And this is a mathematical treatment of statistical information. What's interesting about this is you can compute mathematically how likely it is for something to appear at any point on this chart. Down at the bottom, you've got standard deviations. 0 to 1, negative and positive, is about 65% of all of the samples. And the white part is what we consider average or normal. Red part is warmer temperatures, blue part is colder temperatures. So 65% roughly in one standard deviation. Within 2 standard deviations, you have 95% of all samples. And within 3 standard deviations, you have, I'm sorry, that's 97% in 2 standard deviations. Within 3, you have 99.7% of all samples. 3 100ths fall outside of 3 standard deviations. And then since it's positive and negative, this is like 15 thousandths, right? Am I doing that right? 15 thousandths above 3 standard deviations, 15 thousandths below 3 standard deviations. As I start this, it's going to be 10-year averages starting in 1950. And what you see is that, here we go, we're going through the 50s, the 60s, we have variability, but then suddenly when we get to the 80s, we see this dramatic shift toward warmer temperatures again. And what used to be, 15 hundredths has now become very substantial. And when you look at the total area from 2 standard deviations outward, I mean, that's like a third of all the samples. So it is a dramatic shift, and it is not normal. What's key to knowing about this is that we still have cold temperatures. They're just much less frequent. We still have warm extremes. They're much more frequent. This is a chart of carbon dioxide gas in the atmosphere. It was a scientific measurement made from a mountaintop, Mauna Loa, down in Hawaii. And Charles Keeling started this. His son now continues it. But this is a very important chart which shows the growth of greenhouse gas carbon dioxide in the atmosphere. Measured from Hawaii, because that's a very clean environment where you can separate out any other local effects and make sure that you're getting what is truly a global measurement. Now it has this sawtooth shape because that each tooth, each full cycle up and down is 1 year. And because there's more land mass in the northern hemisphere than there is in the southern hemisphere, then when you have a northern hemisphere summer and plants grow, they consume carbon dioxide and they pull that number down. And then in the winter, when those plants die and they release the carbon dioxide, the number goes up. Again, because we have much more land mass and therefore much more organic material growing in the northern hemisphere than we do in the southern hemisphere. And what you see is clearly a trend of growing greenhouse gases from, at the time, about 315 parts per million to what we have today, which is roughly about 440 parts per million. This chart stops a little bit short, but I think we recently had a measurement of 440 parts per million. I put this red line in there to show you that it is not a linear growth. That red line would be linear. What we're seeing is an exponential growth. In other words, each year we're producing more greenhouse gases than the previous year. One of the things I want to point out in here is that you'll hear people say that carbon dioxide is natural and volcanoes produce carbon dioxide much more than humans do. Well, you all remember Mount Pinatubo in the Philippines when it exploded. It put out a huge amount of gases. Can you see it in there? No. Actually, volcanoes, which are part of a natural cycle of producing and consuming carbon dioxide in the environment, put out about 1% of what humans put out. We put out about 100 times more than volcanoes. Okay, so for 8,000 years, the inflow was balanced with the outflow. Since 1980, the outflow is measurably less than the inflow. Now, why 1980? Well, imagine if you're trying to read your weight on a scale that's in the back of a pickup truck driving down the road. That scale is going to be bouncing back and forth, and you're going to have a hard time reading what your actual weight is. And similarly with the environment, there's a lot of variability in the environment. So you see a natural fluctuation that was big enough to mask the effects that humans were having on the environment. Until 1980, where all of a sudden there's enough extra mass on that scale that even though you're bouncing down the road, you can see it's bouncing in a bigger range, a higher range. And so up until 1980, we had the science to understand what was going on, but we didn't have the measurements to show what was actually going on. As a student of meteorology, and actually I studied climatology before focusing on meteorology, as a student in the 70s, I learned about climate change. It actually had been known for more than 100 years at that point. A couple of scientists in the 150 years ago, when enough science came together to understand the physics of radiation and greenhouse gases and all that, they actually made predictions and said, this is where we think we're going, based on the fact that at the time humans were digging up coal and burning it to generate power. Of course, now we use natural gas and we use oil as well, so we're doing much more of that. But they actually made some calculations that turned out to be accurate, so the science was correct. But in the 70s, when I learned about it, and scientists had begun, since Keeling, had begun talking about it much more, they actually went to President Lyndon Johnson in 1965 and told him this is happening and we should think about what it means for humanity and what we should do about it. And Johnson considered some options. One of them was floating billions of little silver ping pong balls in the ocean in order to radiate more light, to reflect it away from the Earth so that less of it would be absorbed. They considered, I mean, they were just brainstorming. But President Johnson said, well, we've got time. We don't even really see the effect yet. So when I came on the scene in the 70s and I learned about this and I talked about it with my professors, they said, you know, that's a very interesting topic. There's a lot of debate about that because nobody's quite sure how much of a real effect it's going to have on the environment and humans. Well, that changed when in 1980 they were able to clearly demonstrate that we were going outside the bounds. So what does it mean for humanity? Well, here's another Gary Larson cartoon. This is it, Jenkins. Indisputable proof that the Ice Age caught these people completely off guard. And here's Ugg in the outhouse. He set his club outside and he got caught. Caught by the glacier. You all know the story of Corey Stringer, a Viking who died of heat exhaustion. He was practicing, the Vikings were practicing in Mankato. It wasn't particularly hot that day, it was in the 80s, but it was very humid. He exercised, he practiced, and got to the point where, he collapsed on the field. They called an ambulance, revived him, he got up and he walked to the ambulance. They took him to the hospital and he died anyway. They couldn't save him, he'd gone too far. What's important about humidity, you all know what dew point is? So dew point is the limit to how much cooling you could have from sweating. So if the dew point is 55, which is kind of an ideal dew point for air-conditioned air, then you can be quite comfortable just by, you don't even notice, you're not even feeling wet, but you're evaporating moisture. When you evaporate moisture, as you know, if you put a pot of water on the stove and turn on the burner, there's a tremendous amount of heat going into that water to boil it away. It takes a long time to boil off that water. Well, that same amount of heat, when you evaporate sweat, provides a cooling effect. And you can cool, theoretically, down to the dew point and no colder. All right, so what do you think is a temperature, a dry air temperature? Imagine you're in Arizona, where it's a dry heat. How hot do you think humans could survive?
120.
Very good guess, about 120. I believe that the number of 134 degrees has a 6-hour survivability. In other words, you would die within 6 hours if it was 134 degrees. If it's 124, 125, you might be able to survive that if you dress appropriately and stay in the shade and whatnot, right? What do you think is the highest dew point that a human can survive? Well, it's not going to be hotter than your body temperature, because then your temperature would start to rise and you'd cook your brain, right? It actually is somewhere around 92 degrees dew point. Now that's a very high dew point because you have to have the water, the lakes, the oceans, they have to be that temperature in order to evaporate the moisture to produce that dew point. Anything, if that water is colder than that, then the moisture is going to condense out of the air, right? So we are safe for a while, but we're getting to the point now where, for example, the Gulf can be 90 degrees. And we're talking about a situation where if you can't get to an air-conditioned environment, you will die. So humans cannot survive. I mean, we all know about how dangerous it is in Minnesota. If you go outdoors and it's really cold and you're not appropriately dressed, there is no dressing for a high dew point. You have to get inside of a machine-controlled environment. So, you know, with all the things that happen with climate change and the changing patterns of weather around the world that come with it, there are different, effects that are known to be related to climate change, but it's hard to correlate them with high confidence levels. So everything that happens is rated according to its likelihood that it's connected to climate change. For example, hurricanes and tornadoes, there's no clear evidence that says we're going to have more of those, but what is clear is that when we have them, they are more intense. Because that higher dew point, that higher amount of moisture in the air, that is the fuel for storms. That's the gasoline that drives storms. And I won't get into that, that does involve math. But more humidity, more moisture in the air means more intense storms. Well, when it comes to fires, the wildfire season has clearly gotten longer and started earlier than it used to. And this has a very high correlation with climate change. What happens is we get these rivers of moisture and we get a lot of small vegetation. These wildfires are really driven by the small vegetation. So that stuff grows up quickly and then it dries out. And now you've got kindling for a fire. So when a fire starts, it's more intense, it covers a broader area. And here we have a situation where a whole town, Paradise, California, burned down 14,000 homes and businesses. Once again, we have built our wealth on the boundaries based on a stable climate that lasted for 8,000 years, and now it's not stable anymore. So these places where people thought we could live and protect ourselves and be safe are starting to become dangerous places to live. Global surface air temperatures, and what's important about this is that there are parts of the world where, there's that 122 degrees Fahrenheit. We're getting to places where you cannot live, where people have lived and people do live, and now they can't live there. They can't grow food there. They can't survive the environment. So what do? They migrate. And what happens when large numbers of people migrate? You start to get concern, instability of governments as you have large influx of migrants. People get worried, and you start to see the rise of protectionism, of fascist governments around the world as people react to this movement. So it brings an instability in society and leading to wars. There's a very strong correlation between climate change, and I'm not really good at, where's Syria? Somewhere in here? You remember Syria had a civil war, and Assad, he was attacking his own people. What happened was the farmers couldn't grow crops anymore. They abandoned their farms. They moved to the city where they were abused. And that started to create unrest. And Assad, with an iron fist, tried to put that down, and that led to civil war. So there's a case where climate change has a very strong correlation with civil war. Here we have Portland, Oregon. There was this huge heat dome in 2021, this huge atmospheric dome that produces high pressure and high temperatures over the region where that dome is. And that huge dome sat on top of the northwestern part of the United States and Canada, southwestern part of Canada, and created extreme temperatures that they are not used to. In Portland, they don't have a lot of air conditioning. They don't need it. Same with Seattle. Again, we have built our wealth on the margins, and now those margins are changing. When we have tornadoes and hurricanes, they last longer and they are more intense. The rapid intensification of hurricanes has a term that's called bomb cyclones, bomb hurricanes. And that refers to a rapid increase in intensity over a 24-hour period. We had a situation like that with Katrina. where that warm water in the Gulf, with all that humidity coming out of the Gulf, that just amped up that storm very rapidly, and it went from 3, I think, to a 5. You know that Hurricane Harvey, you remember Hurricane Harvey dumped a huge amount of water on Houston, where they had all these properties that all of a sudden they were flooded. You know, a lot of wealth, a lot of housing, and I heard the number for how much they had 54 inches of rain in that storm. That was a new record for the continental United States. It was so much that they had to add colors to the chart to show those high numbers. I also heard the number in terms of gallons. It was 27 trillion gallons. You have any idea how much water that is? Well, I got out my pencil and paper, I did some back of the envelope calculations, and I determined through sort of reckoning that Mille Lacs is 1.7 trillion gallons. So this storm dumped the equivalent of about 17 Lake Mille Lacs on Texas and Louisiana. That is so much water that if you drew a line across the state from west to east from about the level of Coon Rapids, you would have 5 feet of water from there to the southern border with Iowa. That's how much water that is. New territory. This is hail in Argentina. 1.5 meters in 15 minutes. Again, humidity comes with higher temperatures, you have more humidity. That humidity is the fuel for storms. So who's coming to save us? That's a fire truck. Remember back in, again, 2021, all across the South we had extreme rainfall and we had flooding. And what's interesting is during this era, the Noah's Ark exhibit, it had to file claims for water damage. $1 million claim. So that's what's happening in the United States, but there's stuff happening all over the world as well. Here we have Africa where, again, longer droughts because higher temperatures evaporate more moisture. So even though you might have more rainfall, you're evaporating more of that rainfall and you're creating difficult situations for farmers. We have a situation where parents have to leave their children behind and go off looking for a livelihood. Again, they can't live where they've been living, so they're going to get up and they're going to move. You can't expect them to do anything different. This chart shows the desertification of Minnesota right here. As we head toward 2100, although we're getting more moisture in Minnesota, we're not getting it in the same patterns that we used to, so it's not as useful for farmers. But we're also getting more heat, which means it's going to be drier, and what used to be the situation for drought down here is moving up here. And it's changing the way we do farming in Minnesota. All right, what can we do about it? Well, first of all, we have to be open eyes, clear about where we're getting this chemistry from that is filling the atmosphere. And it comes from basically every segment of society, all right? So there's the transportation society, which includes air and ships, the trains and cars. We have the burning of coal and other fossil fuels for generating electricity and for powering industry. We have the way we do farming, where we're digging carbon out of the soil with farming practices, and normally the soil is a huge carbon sink. We're changing that equation, and so there's less carbon stored in the soil and it's more in the atmosphere. What else? Natural causes. Now, the permafrost is basically millions of years, or maybe thousands of years, of vegetation that is frozen, so it's stable. As we warm the planet, we're warming that permafrost, and that vegetation is springing back to life and rotting. As it rots, it produces methane, which is about 20 times more powerful than carbon dioxide, and that methane accelerates the process. It is what we call a tipping point, which means if we push things far enough, it's like pushing a car up a hill. We get to the crest of the hill, we keep pushing the car, and all of a sudden the car starts rolling downhill on its own. And now we have a heck of a time trying to stop that car. So we want to avoid these natural tipping points as much as we can. All right, so these are the major sources, human causes for greenhouse gas accumulation in the atmosphere. Of course, transportation is a big one. It is the biggest one, and this is all kinds, not just cars and trucks, but planes and boats and so on. That is the biggest one in America. It's smaller in other parts of the country where they don't drive as much as we do. Electric power. We're getting better every day with electric power. That used to be the number one, and now it's coming down. We have industrial processes, making steel, making cement, and so on. We have commercial and residential. This is really quite a big one where we're heating and powering our buildings. And agriculture, the way we raise and what we raise, in particular, ruminant animals that use they use anaerobic digestion as part of the way they process their food, particularly cows, where the process of digesting grass produces methane. All right, so we're getting to this simulator now, and this is the third part of the talk. This En-ROADS is, imagine if you could take all of the formulas, all the procedures and processes, including business and economics, and hold all that information in your head, and then compute the effects of any change you make. That's what En-ROADS does for you. You can't do it as a human in your own head. It's too hard, but this is parameterized. It takes all of these different functions that come to bear and makes it so that you can add a number in, and then like a great big spreadsheet in Excel, you can run a simulation and see what's the outcome from that. It's not a model per se, but it takes information from a wide range of models, and like I said, parameterizes it, and then applies the formulas to know what, if we believe those models are true, then what's the likely outcome. It's very conservative in the models that it chooses, kind of picking middle of the road, not ones that are extreme, not ones on either end. And then they started running it in 1990. They ran the clock back and ran it up to 2020 to see if that parameterization and those models that they're working from are good predictors. And when they saw that they could get a good correlation between the first 30 years of running the model, then they set it out there for people like me to use, and we can run it for the next 80 years. So this model runs until 2020. And this is what it looks like. Over here on the left, we have all of the ways we get energy. The bottom one, the brown, that's coal. Red is oil and natural gas. Oil. Red is oil. Blue is natural gas. Green is renewables, like wind and solar, and hydroelectric. Then bioenergy, this is like ethanol or biodiesel. And then nuclear, which you can barely see, is a very thin blue, sort of a teal, light colored blue. And then there's this one called New Zero, which doesn't exist, but what if we figure out, for example, how to do fusion? And you can control all those and say, all right, this is where we get our energy today, but what if I change these values? What if I put a heavy tax on coal, slide it all the way to the left, and put a lot of incentives into building renewables? How will that change things? And we can control it. There's coal, oil, natural gas, renewables, nuclear, this new energy, bioenergy, and then this one called carbon price, which is a way of using economics to steer where we get our energy from. All right, then how we use it. Get transportation over here where we can make it more efficient. Everybody can drive a Prius, or we can electrify it as well. And the same with buildings. We can all have heat pumps, or we can actually get rid of heat pumps and burn more natural gas to power our buildings. So they can slide that either direction, And then we can turn that to where we get the energy from electricity. And why that's important is, as I said earlier, we keep getting cleaner with the electricity. So if we shift from using things like oil and natural gas to using electricity, then as the electricity gets cleaner, we automatically reduce the greenhouse gases. And then down at the bottom, because these are factors, maybe not so controllable, but population. What if we have less population? What if we have more? What if we have more GDP? What if we have less? How will that affect our society? And so those are interesting knobs to play with. And then over here, a couple of more sources. We're cutting down trees in particular to get palm oil in Indonesia, but we're also cutting it down in the Amazon to grow soybeans and other crops for feeding livestock, which then is exported to China and other places. So we're cutting down forests, and then methane and greenhouse gases. Again, methane can come from natural sources, like cows, anything that is a ruminant animal, but also from the releases when we dig it out of the ground, it leaks out of the pipes and so on. And then a couple more ways to get rid of the carbon. We could plant more trees, or we could build machines that pull carbon dioxide out of the air and allow us to store it in the ground. All right, so starting to play with some of these knobs. Oh, and then this chart over here on the right, this is greenhouse gas emissions. It tells you a black line, which is the status quo, and a blue line, which currently matches the black line, and that's what happens when we make the choices, and we want to see how they turn out. And then over here is an estimate of the temperature increase by 2100. We're already at about 1.4 degrees of rise, so this would be an additional 2.2 degrees by the end of the century, given status quo. And by the way, these guys, this organization, which includes lots of really sharp people, they continue to update this. So in the years that I've been using this, I have seen them actually lower this number because they're seeing the effects of having a lot of renewable energy deployment. All right, so what happens? Everybody says, well, all we have to do is stop the moratorium on nuclear, let us build nuclear power plants. That is a green energy. What happens if we pour a tremendous amount of incentives into building up nuclear? And what happens is, well, we save 1/10 of a degree Celsius, a little less than 2/10 of a degree Fahrenheit, and we don't see an effect. This is really interesting, is this shows us also the timing of the effect. We don't see an effect until about 2040. And that's because if we built a nuclear power plant today using some brand new technology, it's going to be many years before the second one is built, because power companies are very conservative. They're not going to step out there until they know that it's going to work out, financially especially, right? And then it takes time. Again, I told you that there's business practices, business knowledge that's built into this, where we know it takes time to build up the supply chain and the expertise, the staffing, the money, everything takes time. So before we can make much progress, we're around 2050. It's 25 years from now. If today we press all the way down on the pedal for nuclear energy. And then what I find very interesting is that it's very limited in its long-term effect. And I believe the reason for that is because it is the most expensive source of electricity that we have. And so we will continue to look for ways to avoid using that expensive electricity. All right, I talked about this carbon price. Now what that is we go to the source of the fossil fuel, the mine or the wellhead, and we measure the amount that's coming out of the ground, and we put a fee on that. We start with a small number, and then every year that fee goes up. And that is a price signal that steers society away. Now what's interesting about this is it happens automatically in the background. You're not telling anybody what they can or cannot do, what they have to buy, what they cannot buy. Everything is free choice, but you've got this rising cost that's built into it. So you'll see innovation where people are going to find ways to avoid using those fossil fuels. The second part of this, in addition to collecting that money, is to not use that money to run the government, but rather to give it back to the citizens. So everybody gets a share. Let's say that the payout is $1,000. I get $1,000, you get $1,000, Bill Gates gets $1,000. Everybody gets it based on being a human, not based on how much money they have, right? And that money has the biggest impact on the poorest people, who might also be most impacted by the rising cost of fossil fuels. But they're going to have that money to help them offset that rising cost. And because it tends that lower income people use less fossil fuels than rich people do, I mean, think private jets and stuff like that, right? Big houses. It's going to be more beneficial for the people at the bottom of the income spectrum, and they're actually going to do better under this program. But that money that they spend is going to drive innovation, and we're going to see lots of exciting new products. And we've already seen a lot of interesting products. And think about LED light bulbs, right? LED light bulbs were originally about $45 per bulb. And very quickly, we've seen that drop to where it's less than $1 per bulb. And since the cost of just powering an incandescent light bulb was about $8, and you save about 7 of those dollars using an LED light bulb, we're saving a lot of money with that new technology. Okay, here's another attempt to make cars more efficient, make planes more efficient. Everything's a hybrid, right? Push that as much as you can, but we're still getting our energy from fossil fuels. And what we see is that, again, we don't have much of an impact until about 2040. And that's, again, because it takes time to change out the fleet. And then the total effect is about 2 degrees, 0.2 of a degree. So then electrify it. We only get about another 1/10 of a degree. So just electric cars by themselves isn't going to solve the problem. It's an important thing to have, but it's not going to solve the problem by itself. How about making buildings more efficient? Turns out buildings are really significant. And there's a lot of low-hanging fruit there. Insulating buildings, changing the way we heat those buildings, sealing them up, and so on. So now we're getting 0.4 of a degree Celsius, and then another 0.2 if we electrify. Again, getting our energy from clean electricity. But now, what's interesting is that we haven't changed how we generate electricity. We're still using a lot of fossil fuels for that. So we're not seeing as much benefit in electrifying transport or buildings as we could see if we also clean up the electricity. All right, how about just controlling methane and these F gases? F gases are, like I said, like Freon. There's one that's used in the electric industry called sulfur hexafluoride. It has a greenhouse effect equivalent to about 24,000 times. So a molecule of sulfur hexafluoride is 24,000 times more potent in terms of greenhouse gas effect than carbon dioxide. So we control those. We make sure we recycle our old refrigerators and such. And we tighten up the pipelines and we try to reduce methane in other ways. That has a pretty dramatic effect. But again, not enough. We want to get this number to 0, or at least status quo, which would be 1.4. All right, how about these machines that can take carbon dioxide out of the air? We hear about carbon capture and sequestration. Have you heard of that? That's where you put a machine at the end of the smokestack, and that machine takes carbon dioxide out of the exhaust stream, liquefies it, pumps it into the ground. That's one way to do it. Again, we don't see much of an effect. Well, actually, we can see that much more quickly. We can see that by, significant effect by about late 20s, early 30s. But then we go to a certain level and we, it doesn't continue to help us. It has a limit. All right, so because I know you all wanted to see if it's possible to do this, I pushed all the sliders every way I could. I want to particularly point out that I changed the carbon price to make that a strong effect. By the way, economists love this solution of all political stripes. They think this is the way to solve climate change. Carbon fee and dividend. Push that, that causes a great explosion in renewable energies and a real diminishment of fossil fuel energies. We push the efficiency of buildings and transportation, and we electrify them. We rapidly cut down on, we stop cutting down trees. We get a hold of these greenhouse gases other than carbon dioxide. We plant as many trees as we can, and we push all the technology we can to pull carbon dioxide out of the atmosphere. Now, what I want to point out here is I also slid the population to the max and the economic growth to the max. And I can still solve the problem with those pushed all the way up. And the reason is, when you decarbonize society, then population and economics are not related anymore. Today, if we produce more, we use more fossil fuels. But if you take the fossil fuels out of the chain, then you can push the economy as much as you want, and you're not going to have this negative effect. These two lines, I changed the chart, now it's temperature instead of greenhouse gases. And there's two lines here, this lower dotted and upper dotted lines. The 1.5 degrees is what the Paris Accord was calling for, that we would try to limit warming to 1.5 degrees. Immediately at that event, these island nations in particular that are very close to sea level, that are already seeing an inundation during storms that they didn't used to see, they're saying, you know what, if you go to 2 degrees, we're done. We can't live on our islands anymore. Would you please try to set a goal of 1.5? So the scientists went back to the whiteboard and they said, well, what are the effects? What are the differences between 1.5 and 2? And they found that a lot of really harmful effects occur if we go that extra 0.5 degree. So now we're talking about trying to limit it to 1.5. And as I said, we're almost already there. We're probably going to hit it somewhere around 2030, early 2030s. If we take all the actions we can, we cap that and we start to go down, but it's pretty much baked in. We're going to cross 1.5. All right. So what's next? Well, first of all, what you all can do is embrace the solutions we already have and expect innovation. Again, that example of LED light bulbs. It used to be that it was a very political thing that we're getting rid of incandescent bulbs. Nowadays, they took away the ban, so you can still buy incandescent bulbs, but who wants to, right? Who wants to? They're expensive, and what do they give you? They generate more heat than light. Electric cars. We're getting a lot of pushback about electric cars, but in fact, worldwide, the adoption of electric cars is 15% market share. It's lower in the United States. We're at about 8%, but that's still a lot of growth. And we're seeing a rapid increase in the adoption of electric vehicles. Is that a bad thing? I don't think so. I drove an electric car here today. I've had an electric car since 2012. And I think they're a lot better than gas cars for a lot of reasons that I'm not going to get in here because I'm running out of time. But I think we need to invite people to the solutions. I don't think you can ask people to make sacrifices to solve this. There's a psychological experiment that was done where people were asked to do something altruistic. And when they'd done that, then they were offered a plate of cookies. And then there was a control group that wasn't asked to do anything, but they were offered a plate of cookies. The people who did something altruistic took more cookies. And that's because we have a natural tendency, we think if we do something good, we should get rewarded for that, right? So if you ask somebody to make a sacrifice, they're likely to then do something to reward themselves that's going to counteract the effect of that sacrifice. There's another experiment that was done where they noticed, it was an observation, not an experiment, they noticed that people who use reusable grocery bags, that remember to take the grocery bag into the store with them, they tend to put more goodies in the bag. Again, they feel like they deserve a reward. I know people, I good friends of mine, they have 5 Priuses. Their mom, dad, and the 3 kids, they all have Priuses. They're so pleased with themselves that they take long trips. And a Prius is a great car, but it's only half as much as the average car. So if you drive twice as far, guess what? You're at the same spot, right? All right, what have you done? I'll bet you've switched to LEDs in a big way. Of course, you can lower the temperature and lower the temperature in winter, raise it in summer. That's kind of a sacrifice for a lot of people, unless you're in menopause. Travel more effectively. Take fewer trips. Be more purposeful when you take trips. Take somebody with you. And look around. When you're on rush hour on the freeway, how many people are in each car? 1. Most people, 1. See if you can share the ride. Move away from fossil fuels today. For the most important reason is you're getting ready for the future, an inevitable future. And talk about it. Use I statements. Say, look, I'm concerned. I've seen, I have experienced, I have enjoyed. And then just share it and invite people into the conversation. Yes?
I just want to add something to that list. Ceiling fans.
Ceiling
Ceiling
fans.
fans make you feel much more comfortable because of evaporation of
That's
perspiration,
right.
I suppose. So you can lower your temperature.
That's right. You can lower your temperature with a fan. Interesting thing about ceiling fans is they have no effect if nobody's in the room. So if you think you're cooling down a room by turning on a fan and nobody's in that room, it actually is warming it up slightly because of the energy that you're burning to run the fan. I have a handout that many of you have taken, and there's some resources on there. If you're interested in spending a significant amount of time doing something, I would highly recommend that you read Catherine Hayhoe's book, Saving Us. We're not saving the polar bears, we're saving ourselves. And she talks about the psychology of talking to people. She is conservative herself. Her husband is a evangelistic preacher, pastor, and he writes. He's well published. They're both PhDs, right? They actually got married before they realized they were on different sides of the climate question. And they had to then, because she's an atmospheric scientist, they then had to reconcile it between themselves. And they found out how to talk about it with respect, with facts, not opinions, with data. And they came to understanding what's really happening and how they could work together on it. So she has taken that to 11.
What's her name again?
Catherine Hayhoe. It's on there, Hayhoe, book Saving Us.
Yes.
If you are interested in doing a book study, I can help you with that. I have questions and answers that I've created to go along with that book. But that's the end of my talk. I also have a little bit I want to say about Earth Keepers. Earth Keepers is a Methodist activity where, oh, come on, where's my... Global Ministries of the United Methodist Church has created this program called Earth Keepers. We're looking for Methodists to lead grassroots environmental projects that are action-oriented, anti-racist, bold, and entrepreneurial. It's a training and incubator program that provides a collaborative space for United Methodists to develop and grow environmental projects in their communities, including eco-theology, anti-racism, community organizing, and project planning. You come to the program, this training, by the way, the next training is in October. It's going to be here at Hamlin in the Twin Cities. So it's an excellent opportunity to participate. These go on around the country, and in fact, at the same time, there's going to be one much farther away. So As a Global Ministries Earthkeeper, you bring a project to the training, and then you will be equipped. You'll get training to help equip you to lead creation care work, to learn strategies for organizing, planning. It includes some opportunities and some instructions on how to apply for grants. You get support and guidance through consultation with fellow Earthkeepers. And you become part of this Creation Care Network, an online community that supports Methodists engaged in environmental ministries. Some examples of projects. You develop a plan for a project that you'll implement in a community with which you have a relationship. And through the training, you'll identify the problem or issue you wish to address and learn how to articulate how your project responds to the problem. So ecosystem health, efficiency in energy and water consumption, environmental justice and anti-racism, the disproportionate burden. By the way, climate change has a disproportionate effect on the poor. The rich can afford to adapt to it, to mitigate it, to basically have air conditioning. Food security, innovation, renewable energy. These are just some ideas. Waste reduction, waste management, water, safeguarding our water. Here's where you can apply for it. I've got, again, some URLs that are on the sheet that I handed out. The training begins in person at Hamlin on October 3rd, but at the beginning of September is when you actually start to do the work. It's about 8 hours of work before you get to the training. I participated in the inaugural training, the very first training that was down south of Atlanta several years ago. Now, those people who were in that first program and have been in programs since then have come together in Minnesota to form this organization called Minnesota Hopeful Earthkeepers. And we are working together to build a movement and network equipped to respond to ecological degradation, extinction, climate change, environmental racism, with love, healing, transformation, and regeneration. So, something to consider. I took a lot longer than I normally do. Thank you for your generosity. I believe we have a little bit of time left for questions. And if you like, we can play with that En-ROADS model. That's another option. What's kind of cool about this is that you all can tell me what you think is the least likely to be an effective solution, and then we can experiment with the simulator and see what it says.
Or would it be least likely to happen?
Least likely to happen, well, that's a political question, but from a technical and reality perspective, for example, planting trees. This was kind of popular a few years ago. It's still talked about to some degree. How about if we really aggressively stop cutting down trees? Interesting thing about planting trees is when they're small, they don't take up a lot of carbon. They have to grow to maturity to get to the point where they take up a lot of carbon. And eventually they reach an equilibrium where a new tree is planted or grows and an old tree dies and decays. And so the amount of ability to take carbon out of the atmosphere plateaus. You also have issues with where do you get the land? You have to incentivize people who have the land, farmers or indigenous people. You have to give them the incentive to preserve the forests in perpetuity. It's no good if they do it for 10 years and then they stop, right? So that's... Any ideas, things people would like to check? David.
I just read about the carbon capture open in Iceland.
Yes.
I'm wondering what kind of effect that's going to have.
Yep.
Doing more of that, you said when you went through it originally, it was not that much.
So that's this slider. This is a little hard for me to do. This slider right here, technical. Incentivize the heck out of that. How much effect does it have? Well, this little thing here is kind of cool. It allows you to cycle through your choice. So, on, off, on, off. That isn't very effective. So, come on. It goes from 3.3 to 3.2. But it's,
So if you would move the carbon price up to the max, what would the price be?
well, that's another interesting thing about this model is you can drill inside of it and see what numbers they're actually using. These three vertical dots right here, when you click on that, you start to see, okay, the assumptions they start with, and they start with what they think is the most reasonable approach. Again, they're not extreme. They're trying to take a middle-of-the-road solution. So they start at $5 a ton, starting this year, and then you can set what you want the final price to be, and when you want that to occur. There's information over here. There's an information button. You can read about this. Countries implement carbon taxes. Emissions performance standards set limits on the amount of carbon dioxide per unit energy. And these are examples of different ways of implementing a carbon fee. Cap and trade. Pricing carbon is a high leverage strategy as it both reduces the carbon intensity of the energy supply and reduces the overall energy demand. When the carbon price is increased, notice that coal reduces the most. It is the most carbon intensive, which makes it the most sensitive to a carbon price. Natural gas decreases as well, although more modestly. Oil decreases only slightly, even though it is more carbon intensive than gas, because it is not easily substituted for other energy sources. Okay? So we can push that slider a little bit, and even with just a little bit, it's pretty dramatic. Push it some more. What's really cool about this is it's comprehensive. You know, it is really implicitly changing all the other sliders.
So that's the most effect of just one of those sliders.
It is the most effective. It is the easiest for the parties involved, except for the politicians who have to try to sell it. Politically, it is not very popular.
What do you mean it's easiest for the parties involved?
You don't have to think about it. If you want to drive a Hummer, you drive a Hummer. You just pay what it costs. You don't have to decide, okay, how am I going to get rid of my incandescent bulbs? You just buy whatever you want. If you want to keep driving a gas car forever, fine. Nobody's telling you you can't. But society as a whole, in the aggregate, is going to move where the dollars take them. I mean, really, we make a lot of decisions based on price, and unfortunately, a lot of the decisions are to try and get the lowest price possible, right? I took a class in college called linear optimization. It's used in business, and it's a way to figure out the cheapest way to do something. And the example we had was ice cream, okay? So you had one way to make ice cream. You take sugar, cream, flavor, fruit, whatever. Pretty simple recipe for ice cream. Then you come in and you say, well, you could get your fat from, this source or that source, and everything is rated. This is this percent of fat, that's that percent of fat. And then there's different ways to get sweetness, not just sugar, You can get it from corn syrup, you can get it from a lot of different things, right? So you put all these parameters in there, push the button, and it comes back and it gives you a price. And the price comes down, but the ingredients go bizarre, right? I mean, you're making ice cream with lard, and theoretically it will taste the same, and you'll save a few pennies, right? And sometimes that's all it comes down to, is just those few pennies, which when you do things on a large scale add up to a lot of profit, and that's the motive for doing it. But it can be very harmful for us. We are making decisions to save, to get the cheapest price, the Walmart price, and yet what we're selling, and it's like Jack and the Beanstalk. We give up the cow for the beans. Jack got lucky, but I don't think the rest of us are going to see a golden goose in our backyard.
I was looking at the one that says agriculture emissions,
Yeah.
and then waste and leakage. How do you speak to agricultural enterprises to get them to buy into that? Because like you said, it has to do with money.
Right. Interestingly enough, again, not to make a sacrifice, but rather to come out ahead simply by making the choice, we're seeing farmers do what they call no-till farming. And slit, where they instead of plowing a field and turning it over, they're cutting a thin slit where they drop the seeds. And they're finding that they can manage their farmland more effectively, spending less on pesticides and having less energy input into the farming practices. So that's one way to do it. Simply not turning over the soil and allowing that carbon to be captured in the soil. When you grow a plant, the roots go down into the soil. If you cut off the plant and it dies, those roots stay in the soil. And that's a way of sequestering carbon. When we turn that soil over, we expose that dead organic material to the air, and it starts to release its carbon. And that's what we've been doing. So, if you look at the way we grow corn in particular, the soil is sterile. There's almost nothing left in it in terms of microorganisms that convert minerals into nutrients for plants. Instead, we dump fertilizer on it. We put all these additions onto it so that we can grow it in the soil. It's hardly even soil anymore, it's more regolith. That becomes kind of just an environment in which you could support all these artificial activities. So farmers are already moving to that, and many of them are finding a lot of benefit in doing so. And so that's one way. As consumers, we can cut down on eating things that have a big impact. And beef, unfortunately, has a big impact. Because when cows digest their food, they generate methane, they burp that methane out. It comes out the front, not the back. They burp that out, and we add a lot of methane to the environment. Switch to pork. Pork is much lower greenhouse gases. Or to chicken. Chicken is even less. You know what's the lowest? Crickets. I've tasted crickets. Not bad.
Tastes like chicken.
Tastes like chicken.
I have a question about methane. My understanding is garbage creates methane. And
Anaerobic digestion.
how about composting?
Composting is aerobic, and it does not. Composting produces carbon dioxide. There's no getting away from that, but it doesn't produce the methane. Methane, if you've ever had a pile of wet material in your yard and you go and you kick it, and it stinks to high heaven, that is anaerobic digestion. It's growing in an oxygen-starved environment, and the biology of that produces methane. So composting involves a lot of oxygen. In fact, professional composting sites have machines that just go down the rows and turn it over to mix oxygen into it. And same thing in your yard, if you've got a pile of leaves and you turn it over and you get more oxygen, more air into it, then it will decay aerobically, which is much better for the environment. But yeah, take the garbage, don't throw your food waste in the garbage. Put it in a composting bucket and take it to a compost site. And I understand maybe over here you have collection.
Yes.
Yeah, absolutely wonderful. For that reason, but also for the reason of needing less landfills, which is another problem that is threatening society. Overwhelming landfills.
I have a question about artificial intelligence.
Yeah.
I have heard it uses a tremendous amount of
A
electricity.
tremendous amount of electricity for artificial intelligence. The learning process is very compute intensive, and it uses the fastest processors that companies are building. And there's this relationship between power and speed in the computing industry. So we're not taking the most efficient chips that you might find in a laptop. We're taking super power hungry chips. We're building great big machines because we want to get the answers in a time frame that we can use them. But yes, the training process for AI involves a huge amount of computing. Once the model is trained, then it takes less energy to run it, but we're continuously training them. So, a single AI data center can use all the power output of a single power plant. Like you have up at Becker, can take all the power for a single power plant in some of these super big AI projects.
I have a question for you.
Yeah.
You've been showing us wonderful educational data and scientific simulations. How do you see the human factor, and how have we been doing as a society? Are we moving towards curbing these things? Are you hopeful, or are you, give us just a read overall, like we better hurry up and go, or now we're making good timing? What's your sense of the macro movement and the human equation?
It's really human nature not to solve problems until they're problems. We can foresee them coming, but we keep thinking that we still have tomorrow, and we can solve it tomorrow. So I see us inevitably addressing this problem to a greater and greater degree each day, but always too late. I shouldn't say too late, always later than optimal, because it's never too late. Think of an airplane trying to take off while you're building the runway, right? That airliner starts down the runway, and you're working as fast as you can at the other end because you know it needs X amount of distance before it can take off, right? If you can forestall that airplane a little while, or get it to come down the runway a little slower, give yourself time to make the runway longer. That's kind of an inverted example, but what I'm trying to say is, everything you do today, none of it's going to solve climate change by itself, but it's going to make that runway longer. And that's going to give us more time to develop the solutions we need, and more time for society to move. When you think about how corporations work, the heart in business is only for pumping blood. They're all about producing the maximum return on investment. Sometimes that means doing things that are good because your customers want them. And in order to keep your customers, you do them. But the reality is, a CEO that says, well, we'll make less money, but we'll be better for the environment, is probably not going to be the CEO tomorrow. So asking corporations to solve this is not an effective way to address it. Rather, we need policies where we as citizens say, all right, the most important thing is people. So for people, we're going to set these policies in place, and we've seen some of that. We have a really excellent standard for generating electricity. where we've said we're going to have 100% clean energy by 2040. And you know what? Power companies, in which I play a part, I'm on the board of Dakota Electric, they said, okay, we can do that. As long as you make it so that it's a level playing field for everybody, yeah, we can work in those environments. So we need to change that. We need to create a playing field that has a solvable future. And that's where talking about it is so important.
And we appreciate you talking about it with us. Let's show a little appreciation here. Wonderful job. We appreciate that. I'm just like overwhelmed. So thank you for enlightening me, and I'm sure many who are here. All right, you have lots to think about. You have lots to pray about. We are people of faith that say, hey, we still believe and have hope. I'm going to refer you, I think, back to last month's newsletter. Maybe it's the current month's newsletter. I think I had a little story in there about a king who, I don't have to deal with this until it was too late. Now I think we need to wake up and go, don't be putting it off. We do have a responsibility right now. So, thank you.
Thank you.
We have one more week. We'll see you next week. We will wrap it up then. I know Reverend Cooper Wiggin will be back, and he will be also talking about, well, what can we do? I think is where he's going with all this. So come back and we'll wrap that up. Next week, we're also out again with another Take a Hike. So feel free to join us there as well. Thanks for coming.
Thank you.